Hello and welcome back to Calculus 3, section 15.3 on partial derivatives. So we are going to establish two partial derivatives right now, one in direction of x-axis and the other one in direction of y-axis. So if I am to, red, there we go. So if I am to draw some type of a surface and x, y, and I don't like this again. So let's go like that. So there is some kind of a surface, and if you have a point AB in a domain, so this is point in the domain, that point will find its equivalent point here on the surface, and that point would be A. I don't want to do that there. I'm going to move it. So this point here, I don't want to use red either. I'll point, no red. I'll point to it and I'll say this point is A, B, and then f of A, B, right? Because you are calculating z by plugging in x, which is x equals A, plugging in y, which is y equals B, and you calculate z equals f of A, B. So this surface is z equals f of a, b, our function from last class. So we have the surface z equals f of a, b, and then you have some kind of point in the domain, which is a, b point in the domain, and that one is going to create a z on some elevation, and that's a, b, f of a, b, which gives us the top. So now, when you have that, we are going to draw over here in let's say blue. I'll draw, this is like a new y-axis, and I'll draw in red new x-axis. So now these will cut and be some kind of wavy, whatever, right? Whatever the cuts are on the surface. And this is where we are taking the derivative. So we are going to have two partial derivatives. There is going to be partial derivative in x direction, denoted as fx or denoted as partial f partial x. So it's this kind of curved d. You have a lowercase d, and then you have the lowercase curved d. It is not a 2. It is a lowercase curved d for those partial derivatives. And then we also have partial derivative in y direction, which is fy, which is partial f in respect to y, partial y. Now the formal definition, which is something that our honors need to be able to show, which is exactly the same as Calculus 1. So the formal definition is that partial derivative fx is given as the limit h goes to 0, and now since we are measuring the change in x, we are going to have the change in x, that x plus h, and the y's are just going to be tagged along. So we'll have f of x plus h comma y minus f of xy divided by age. So this is, as you can see, it's the same definition like in Calc 1, except you have comma age in each one. Comma y, sorry, in each one. And now for partial derivative in respect to y, limit h goes to 0, you have f of x comma y plus age minus f of xy over age. So this one is just in terms of y. And this is the formal definition. Now, obviously, we don't use these. These are just there to define things. We use those shortcut methods you guys learned in Calculus 1. Now, the way to take the derivative is you ignore other variables if they are multiplied or divided into the variable you are taking the derivative of. And if they are in separate term, they act as constants, and the derivative of them would be 0. So if I have a function f of xy is equal to 3x squared y plus 4x to the 6 minus 3y squared plus 9. This is a good function for us to see the way these things work. So if I want the partial derivative in respect to x, which is partial f partial x, it's important to know both notations. We will use both of these notations, so please make sure you are comfortable with both. This is Leibniz notation, so we'll need it. All right, so when I'm taking the derivative, if you just watch at first and then later you can write it, it's going to be fairly straightforward. Taking the derivative in respect to x, that means that 3y is a constant and derivative of x squared is 2x. That's your calculus 1. So the derivative of x squared is 2x. And the rest is a constant, which is 3y. So you take that in there, plus the derivative in respect to x, that's going to be 24x to the 5, and then minus 0, and then plus 0, because there are no x's in these terms. In respect to x, these terms are constant, therefore they all go to 0. So if you are taking the derivative in respect to x, you hold y as a constant. And in some cases you get to copy it, and in some cases the derivative of it is 0, because this whole term is a constant term, because we are taking the derivative in respect to x. So finally, fx, which is partial f partial x, is given to us as 6xy plus 24x to the 5, and that's the end of the story. So this is our derivative for partial derivative of the function in respect to x. Now fy is partial f partial y, and that is going to be now x is being held constant, which means 3x squared is constant, and derivative of y is 1, so I'll just write times 1, so we know, plus a 0, because there are no y's in 4x to the 6, minus 6y, that's the derivative of 3y squared, and then plus 0, because it's a 9, right? Either way. So finally, partial derivative in respect to y. This y is a small subscript that goes on f on the bottom. Partial f partial y is going to be 3x squared minus 6y. So now you have, from the same problem, you have the partial in respect to x and partial in respect to y, partial derivatives, and they are 90 degrees to each other. One will show, this derivative will show how much change you have in the x direction, where the point is, and this one shows how much change you have in the y direction. So now if you give me the point, let's say the point is, I don't know, 1, 3, you give me 1, 3, I can plug in 1 and 3 in these equations and come up with the number. And that number is the slope of the line, which shows how much instantaneous change you have at that point. how hard is to climb the hill or how easy is to roll down the hill. So these are in general function, and now we can compute x and y direction slopes if we have point AB given. In parentheses, just plug in. Just plug in. And that will give us the slopes in the x direction and in the y direction. So let's take a look at some, a little bit spicier examples, not too much. Say you have fxy given to be x squared sine xy. Which derivative is easier to take in this case? Partial x or partial y? Y. That's correct. Partial y is much easier. Why? Partial x has what? Yes, the product rule. Partial x has a product rule. You have a function x squared times the function of sine of x as well. So fx is not as friendly as partial y in this case, because we only have one y. That means no special rules. I mean, you still have a chain rule, but product rule is, so copy the first, x squared, times the derivative of the second. Now the derivative of the second is cosine of xy, and then times the derivative of the inside. The derivative of xy is y, because the derivative in respect to x is 1 for x, and then y is a constant that multiplies. Plus, copy the second one, which is sine xy, times the derivative of x squared, which is 2x. So now this mess is x squared y cosine xy plus 2x sine xy. Yes, you can factor out x, but we don't achieve a lot with it. So, product rule. In this case, because we had x squared times sine as a function of x. Now, partial derivative in y is much easier, because all x's are constants. So you copy x squared, that's a constant. Derivative of sine xy is cosine xy times the chain rule x that comes out, because it wasn't just sine y, it was sine xy. So think of it as sine 3y, right? If you have sine 3y to take the derivative of, you would call that cosine 3y, and then the derivative of the inside would be a 3 that goes in front. This 3 is actually this x, right? So basic Calc 1 chain rule helps with these, still applies, but now it's not just on numbers, it's also on variables. Because if you're taking the derivative in respect to y, x is held constant. And this is the way we deal with constants, right, in the chain rule. So now we can just simplify this as x cubed cosine xy. And we have our partial derivative in y. So product rule is possible, to run into. And, you just grind through it. So hopefully so far we understand that these partial derivatives are just a little bit trickier than the regular derivatives, and we hopefully understand that each one of these, right, works in the particular direction that you are pointing in. So that's that. The next part is higher order derivatives. Higher order derivatives. Well, there is a second derivative and the third partial derivative and the fourth and the fifth and so on, just like you had first, second, third, fourth derivative when you did regular stuff. But in addition to that, there is also something that is called the mixed partial derivative, which we also need to discuss. But let's first talk about higher order derivatives on the basic idea. So we know there is a function, then we have the partial derivative x, then you will have partial xx like this, and then fxxx, that's the third partial derivative in respect to x, and you can go as far as you want. The same thing happens for the y derivatives. You can have partial in y, and then second derivative, two derivatives in y, 3 in y, going on forever. Finally, you can have a function and then partial derivative in respect to x, and then look at this. You took the first derivative in respect to x, but the next one is taken in respect to y. This is called the mixed partial derivative. Mixed partial derivative. Now let's take a look at some of these creatures. So say you have f of xy to be a happy xe to the xy plus 3y squared minus something. What should I put here? How about something that will be annoying, 1 over x. So it keeps looping. Okay, so what do we get? If you want to do fx, well, fx, you have a product rule again on these e's, because there is x times e to the x. That's a product rule. So we have to deal with the product rule there. That's x, copy the first. The derivative of the second is e to the xy times y as the chain rule. Plus copy the second one, exy times the derivative of x is 1. Plus 0, and then plus 1 over x squared when you take the derivative of 1 over x. So the first partial derivative works out to be x y e to the xy plus e to the xy plus 1 over x squared. That is your first derivative. Now you want to find the second derivative in respect to x. So that's xx. The first one signifies the problem you already did, right? So now you're just working on the extra partial derivative. So now you have to take another partial derivative in respect to x. Well, the first one is still product rule. The second one and the third one are not product rules. So we copy the first, which is xy, times the derivative of the second, e to the xy times y, plus e to the xy, copy the second, times the derivative of the first. The derivative of xy is just y, because x goes to 1, right, as in a derivative. Plus e to the xy times y, and then minus 2 over x cubed when you take the derivative in respect to x for 1 over x squared. You can do that as x to the minus 2, and then minus 2 drops, and minus 2 minus 1 is minus 3, and so on. So now we have our second partial derivative. It's a mess, but it's a derivative. Plus, oh, I have these two terms that are the same. So that's just going to be 2 of these. Nice. And then minus 2 over x cubed. Nice. These two terms are the same. Great. So now we have our second partial derivative. Can you find the third one? Yes, and the fourth one, and the fifth one. So for the third derivative, you will take another product rule here, no product rules on these two. And you just keep going. How far? Well, until you need to. So, copy the first, xy squared, derivative of the second, it's going to be times y, plus copy the second, xy times the derivative of the first is just y squared. Plus, over here we have 2y e to the xy times y, and then we have plus, this is going to be 6 over x to the fourth. So the third partial derivative is going to be xy cubed e to the xy. Now, are these the same? Yes, they are. Y squared, so plus 3y squared e to the xy plus 6 over x to the fourth. You can go as far as you want with these. Clearly, much easier if you had to find fy, right, the partial derivative with respect to y, because no product rule anywhere. And this term also dies completely because it has no y in it. So the derivative in y, in this case, would be much easier, at least for one step. So what do I have? I have x e to the xy times x, because the derivative in respect to y, x is a constant that pops down, plus 6y, and then minus 0, because 1 over x in respect to y is 0. So we have our first derivative here, and that will be x squared e to the xy plus 6y. And now you have the second derivative, which would be off of this one. And again, no product rule, nothing special going on. So we just have x squared e to the xy times, again, another x plus 6, which is x cubed e to the xy plus 6. Third derivative is just a string of these that goes into x cubed is a constant, e to the xy times another x, which is constant from the chain rule from the exponent, and then plus 0 for this 6. So we get x to the fourth e to the xy. Again, go as far out as you need to or want to, fourth derivative, fifth, sixth, and so on. For higher derivatives, things get interesting when you have mixed partial derivatives. So we took our first partial derivative in respect to x. We got that fx is equal, I'm just going to copy it. So copy your simplified version of the first partial derivative. You select like this and you just push copy. Is that how you copy things? There we go. Let's put it here. Mixed. So now I have my partial derivative in respect to x. The next one I want is in respect to y. So we already have a first derivative in respect to x. The next one is respect to y. Oh, look at that. I have a product rule now also in terms of y, so I have to deal with that as well. Copy the first times the derivative of the second, which is e to the xy times x, because I am taking the derivative in respect to y, so x is a constant that pops down. Plus copy the second, which is e to the xy times the derivative of the first, and that is just going to be x because we are taking the derivative in respect to y. plus another one of these, e to the xy times x, and plus 0, because there is no y's in this last term, so we don't need it. So fxy turns out to be x squared y e to the xy plus 2x e to the xy. That's the mixed partial derivative. For the third derivative there, you can take derivative in respect to x or respect to y. Depends on your application. We are going to use this mixed partial derivative when we do our optimization problems at 15.8, I believe, or SEM. Remember those word problems you guys had when you have to find the min and the max in Calc 1? We're going to have the same problems in Calc 3. Those problems where you used to set derivative equal to 0, right? And then look for your min and max. Now you're going to set your first partial derivatives equal to 0. And you will use the second derivatives, including xx, yy, and xy, in a formula to do the second derivative test to figure out whether your point is min, max, or saddle. So this xy derivative is very important. We are not going to go past the second mixed partial derivative. We are definitely going to use this in 15.8. You will use this later as well. But for the purposes of the lecture now, you can have xyx, xyy, xyxyy, right? So it depends on how many of these you want to chain after it. What I want to do now is I want to go into my f of y here, and I want to find the mixed partial derivative fyx. So I'm going to copy this one. No. Oh wait. Going to copy this one. So we are starting with fy now. And I want to find fyx. So try this on your own. You have the derivative of y already. You just need the x. So try this exercise. And we're going to conclude something cool. All right, so we have a product rule on the first. So copy x squared e to the xy times y, because that's our chain rule. plus copy the second one, e to the xy, times the derivative of the first, 2x. So now f of yx is going to be x squared y e to the xy plus 2x e to the xy. And what are you noticing? There is a theorem that says that the mixed partial derivatives are the same, regardless in which order you take them. You can do xy or you can do yx. Right? So that's going to be a theorem that will be very helpful later on, because there was a much more mess in this case to solve fx then y then x. So we take it as a mixed partial derivatives assume that f is defined on the open set D of R2 and that fx and fy are continuous throughout. Then fxy is equal to fyx. So that's a theorem that will greatly help you later on reduce your calculations. So theorem says, assume f is defined on an open set D. That means it has a domain in R2, right? And that fxy and fyx are continuous on D, then, and the major part here is to say fxy is the same as fyx. So you get to do this calculation in any way that it's more convenient to you, whether it's x partial derivative in respect to x first or partial derivative in respect to y. So the last theorem is the theorem that you have the same one as in Calc 1. And then I need to discuss notation a little bit, and we are done. So this is called a theorem 15.6, but I'm just going to call it theorem here. And I'm just going to say if a function f is differentiable, then it's continuous. So if a function f is differentiable at some point AB, then it is continuous at AB. Then it is continuous at AB. This is a nice little shortcut for us in some cases when you need to show continuity for a problem. It's much easier to say, well, I can differentiate, and differentiation implies continuity. So it's a hack way to get, instead of doing the proof for continuity, you just get to state this theorem, and you are done because the function was differentiable. So notation. And this will again contain another example for the derivatives. So let's say you are taking the derivative of, so your f of xy is given as sine xy minus ln y squared. Nah, just ln y is good enough, because the square you can just put that in front of ln. So ln y is fine. All right. So we saw that the notation fx, and we said, okay, so that's going to be the derivative of sine is cosine, so cosine xy, and then the y is a constant, so that jumps in front. And since it's a partial in respect to x, there are no x's here, so it's just a big fat 0. Now, there is the other notation that you can use, which is Leibniz notation, and you can rewrite this as just simply saying partial f partial x is equal to, and you have same y cosine xy. So that's another way to denote the same thing. But as you can see, no matter which notation you use, you have to go into two separate lines. The line on top shows the function, the line on the bottom shows the derivative, no matter which one of the two methods you use to denote the derivative. But Leibniz notation, just like in Calc 1, can be used to put this and this in the same line. So let's do that. If you use partial derivative in respect to x of, and you put sine xy minus ln y inside the brackets, then you can just write its derivative in line. So you either get to use a two-line notation or one-line notation. So it's one or the other. Now you are not allowed, obviously, to put function over here and then you say equal and you put derivative there, because function is not equal to its derivative. Those are two different functions. Unless you just have a vanilla e to the x. In that case, that's the only one whose derivative is its, right? It's the function. Further, if you want a notation, one-liner notation for a second derivative in x, then you guys will have partial derivative squared of partial x squared. So now you see two x's in the bottom because they're squared, right? So you have x and x again. Of sine xy minus ln y. And now, this is partial in x and then partial in x of sine xy minus ln y. So as you can see, the inner problem here is just your first derivative, and then on that derivative you will apply another one for fx. So the notation there for these squareds, because you're going to run into these notations, and it might get confusing, especially if you go to look for the web resources and you talk to a tutor or someone. Not everyone will use the same notation, so it's important to understand notation and which way the notation works. So now from the first one you will copy the partial respect to x that is on the outside, and then on the inside you will have your y cosine xy, which is the answer for this, and then you are taking one more partial in respect to x, which will give you negative y squared sine xy, right? Because the derivative in respect to x will give one more y out, that makes y squared. Derivative of cosine is negative sine, so they all work together. So that's the notation bit, so we are not having an issue with this. All right, so this is the partial derivatives. Partial derivatives give you only the change in respect to x-axis and the y-axis at the point you're observing. So you make a new coordinate system there, and then you can only look at the change going up and down, right, which is the slope of the line, in respect to x or respect to y, depending on which one of these. Now, tomorrow or the next day, depending on the situation, you will see directional derivatives. Now, those will give you the derivative in any direction, and you have to specify that direction with the vector, obviously, because vectors have direction. So we are going to see those very soon. Bye.